Today our topic is arc measures and chord properties. So, learning target, how can I use angle measures to find an arc measure? And how can I use relationships between arcs and chords in a circle? Alright, lots of vocabulary for us. Central angle, an angle whose vertex is the center of the circle, kind of in the name. Minor arc, part of the circle that measures less than 180 degrees. And the measure is the measure of its central angle. So you guys have a nice image to the left of the box. Mine is down here. So right here we have this minor arc. It's less than 180 degrees. So if we were to say the measure of this angle was 40 degrees, then the measure of arc AB would be 40 degrees. It would have the same measure. For a major arc, it's the difference between 360 degrees and the measure of the related minor arc. All right, so if we go back down to that image, our major arc is the leftover piece. It's this blue circle right here. So it would be the difference of 360 and 40, which would be 320 degrees. Now the reason for that is because the degrees in a circle is 360 degrees. That's why they say if you spin 360 degrees, you spin in a circle. You do a whole circle. All right. Semicircle is an arc with endpoints that are the endpoints of a diameter. So it's half of a circle. So it measures half of the degrees of a circle, which would be 180 degrees. Adjacent arcs are two arcs of the same circle that have a common endpoint. The measures of adjacent arcs can be added. You can add the measures of adjacent arcs together. Congruent circles. Circles that have the same radius. So if two circles have the same radius, both a radius of 4, then they would be congruent. Congruent arcs are arcs that have the same measure and are the arcs of the same circle or of congruent circles. All right, and the other picture that you guys have would be a picture of adjacent arcs. So we have arc AB and arc BC are adjacent because they share endpoint B. And we can sum the two measures. First example, identify the given arcs as major arc, minor arc, or semicircle, and then find the measure of the arc. So first, we want arc TQ. We look right there. The measure of its central angle is 120. So the measure of arc TQ would be 120. It's less than 180 degrees, so it is a minor arc. Next arc is arc QRT. So we have arc Q, R, and then all the way to T. So it's in green. So that is opposite of the minor arc, QT, or TQ. So the measure would be 360 minus 120, which would give us 240. So we can say the measure of arc QRT is equal to 240 degrees, and it is a major arc. And now we want arc TQR. So I'm going to draw that in red. So it is two adjacent arcs being added. So arc TQ, which was 120, and arc QR, which measure would be 60. So we would add those two together. 120 plus 60 would give us 180 degrees, would be the measure of arc TQR. Since it does measure 180, it is a semicircle. Example 2, tell whether the indicated arcs are congruent. So if we think back to our definition, congruent arcs have to have the same measure. And they have to come from the same circle or congruent circles. So those are the two things we need to be looking for. Same measure, and are they from the same circle or congruent circles? So arc CD, right here in red, and arc EF, this other red arc. First off, do they have the same measure? This would be 80 degrees from its central angle, and this would also be 80 degrees. So they have the same measure, and they lie on the same circle. So since it fits both those categories, we can say yes, they are congruent arcs. Second example, we have arc RS highlighted in red and arc TU also highlighted in red. They have the same central angle of 90 degrees, so they are both a 90-degree arc, which means they have the same measure. So that's one piece. However, they do not come from the same circle, so we need to know, is this circle have the same radius as this circle? And as you can see, they do not. This circle has that radius, but then for the second circle, it extends farther out, which means the radius is not the same length, so not congruent circles, which means we can say no, they are not congruent. All right, just a couple memes for you as we're going into the diameter of a circle. Particularly like this one right here. What do you get if you divide circumference of a jack-o'-lantern by its diameter? Pumpkin pie, because circumference equals pi times diameter. You divide that by diameter. All you're left with is pi. And a jack-o'-lantern is a pumpkin. All right, hope you enjoyed that. Next example, Theorem 10.4. If one chord is a perpendicular bisector, let's break that down. That is all the way back into chapter 1. Perpendicular means they form a 90-degree angle. Bisector cuts in half. So if one chord is a perpendicular bisector of another chord, then the first chord is a diameter. All right, so if we look at our example, chord QS cuts chord RT in half, so it bisects it, and then we also have that nice 90-degree angle. So the chord that's cutting it in half, chord QS, is the diameter. So identifying diameters in example 3, determine whether AB is a diameter of the circle. Explain your reasoning. So let's look at AB. Does it cut the other chord in half? If we look, 6, 6, it does. It cuts it in half. So we can say cuts CD in half. So it bisects it. Are the two chords perpendicular? Yes, they form a right angle. So we can say perpendicular to CD. So since it is perpendicular and it bisects it, we can say yes, AB is a diameter. For our second example, first off, if we look, we see that nice right angle forming. So we can say that AB is perpendicular to CD. Now we need to know, does it bisect the segment? So we know this piece is 3. We don't know that piece, but I see a nice little right triangle. And we're back to Pythagorean theorem again. So we have a squared plus b squared equals c squared. 9 plus b squared equals 25. B squared equals 16, which means b is going to equal 4. So if we have 4 over here and 3 over here, it does not bisect CD. So we can say that AB does not bisect CD, which means that no, it is not a diameter of the circle. It would be close to a diameter, but not quite. All right, last example for you guys. Theorem 10.5. If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord in its arc. So it's backwards. If we know we have a diameter and we know it's perpendicular to that chord, then we can say it cuts that in half. So in example 4, find the value of x. If we look, we have a chord that's going through the midpoint or through the center of your circle. So we can say that BD is a diameter. It also is forming a right angle with the chord. So since we have a diameter and a right angle, we can say that this segment and this segment are congruent, which means their measures are the same. So we can say that 4x is equal to 3x plus 7. Solve for x. We get 1x, or just x, equals 7. All right, that's all the notes I have for you to do. Thank you for watching this video, and please subscribe to my YouTube channel.